Last time we introduced the concept of vectors. Today, we're gonna put that concept into application by introducing the concept of linear transformation. When a group of objects called vectors sets together, they form a vector space that is closed under addition and scalar multiplication. To make it simple, let's take a look at a small example. Consider this polynomial set of vectors. Remember, a vector can be anything that obeys the 10 axioms, and the polynomials do obey them. The set of polynomials with degree less than or equal to 2 is clearly a vector space, since adding two polynomials of degree 2 and multiplying a polynomial of degree 2 by a constant won't make it a polynomial of degree 3, for example. So it's closed under the two operations of vector space. Now, let me show you the beauty of that concept. One of the places wherein vector spaces appear is in linear transformation. Linear transformation is simply a function that takes a vector as an input from a vector space, of course, and throws another vector in another vector space. That means we can have a transformation that takes a polynomial vector, for example, and gives us a function vector. That's the beauty of mathematics. We can always relate between different things. Now, linear transformation is a powerful function that obeys the below two rules. Plus, it preserves linearity and the origin. For the sake of simplicity, we're gonna consider some examples in 2D. For the first example, if you notice, this transformation has preserved the lines and even the origin, like the vector 2i plus 2j still starts at the origin 0, 0. What this transformation really does is that it copied what was to the right of the y-axis to its left. However, mathematically, we'd like to study the basis, which are the I and j vectors. Where did they go? How are they affected? If you notice, here the j vector is still the same, whereas the I vector got scaled by -1. So we got the following two new vectors. Let us put them in this format for now, and we're gonna define it in the future. Now consider this transformation and watch out, where do the I and j vectors go? Actually, the I vector is transformed to the vector -1, 1, and the j vector is transformed to the vector -1, 3. Now, let's arrange that in a fancy way. Well, we have this transformation. It takes as input two coordinates of a vector, and it produces another vector. For example, if we input the vector 1, 1, and we do matrix vector multiplication, don't worry about that for now, we get the vector -2, 4. What this is essentially saying is that if you want to know the output of any input, you just need to know where the bases go. That's great, isn't it? For more about vectors, stay tuned. Thanks for watching, and don't forget to hit the like and subscribe buttons.